So hi everyone, good morning. Welcome to the first session of the third day of the last day of the conference. For this morning session, I'll share about this test harness that we created for continuous testing on hardware. So I'll start with an overview of what it is and then go into the details, the context, the motivation, its design and development, and its current functions and the future of this test harness. But before any of that, I'm Julia. I'm a software QA engineer at Analog Devices, working with a team located all over the globe for the maintenance and development of this fully automated hardware test harness. My day-to-day usually involves looking into bugs and solving issues that I hate to admit I myself introduced one too many times. And my team in the Philippines, we started as a dedicated QA team for the company's embedded Linux OS. And today we also function as software test lead and take a lot of automation development work based on what we have done for the test harness. And I keep saying we because what I will present is not just my work, it's a collective effort from a large group of people from different locations. When I graduated with a degree in electronics engineering, and I was so sure that I wouldn't find myself working in a semiconductor company because I preferred working on software, working on code, programming, and not really on the hardware side of things, but still I went to this job fair in my university because I was after the free donut they were giving away, and 5 years later, I get to share what we've done with everyone. So I like to run, and one of the first things I added to my conference schedule was the 5K yesterday. So if you haven't had the chance to run around Denver, it's not very easy because of the altitude, but it was a nice run. So that's me, and what about this test harness? There are two aspects to this test harness. One is the hardware infrastructure. And if we could look past the could-be-better cable management, it's a collection of FMC cards that the company produces, evaluation boards. And some of those FMC cards have signal sources or sinks depending on their function, if it's an ADC or a DAC. And then those FMC cards, like the blue ones, that's the one the company makes. And then they're attached to FPGAs. And all of that, those FPGAs are connected to Intel NUCs we use as agents. And all of these, whenever possible, are connected to the network. That's one side. The other is the software, the software infrastructure. And these are the tools that we leverage, the existing tools we use, as well as the tools we created to make use of the hardware infrastructure. So this is our organization in GitHub, so you can see all our tools there. So we have tools for controlling the signal sources, the sinks, and we also have tools for interfacing and interacting with the board. Several others just to make things a little bit easier, smoother, scripts, so everything's there. So putting together the hardware and the software infrastructure, we made it possible to integrate testing on hardware to CIs, such that after building, the artifacts get pulled, they get loaded to the board, and then they're validated to make sure that it doesn't break the functionality of the hardware. Relevant information is tied to the test result, including the commit an artifact was built from and the automated test results generated from the pipelines. And results get reflected back to the commit if we have access to the repos, and some pipelines have their own dashboards, and everything is published there. Using this test harness, developers don't have to worry about bringing the board to a certain state to be able to use it, or configuring it a certain way, or even interfacing with it in a specific environment, because all that work has been absorbed by the test harness or by the tools. Just to give us a background of why we had to do this, it was primarily created for Analog Devices ARPA-OS-based Linux called Kuiper, which has support for over 110 of its products. So our teammates, so this is the roadmap, sorry, not that. This is the roadmap quite literally visualized. So our teammates in Cluj, they handle the builds, and once that's ready, it gets uploaded somewhere so that our team in the Philippines will have the chance to download it, and then prepare it. We have to prepare the SD cards for it. We have to etch the image the SD cards. And while we're doing that, we have time in the background, you can see there. While we're waiting for the SD card to be ready, we set up the hardware, connect all the cables, plug in the FMC, and just really setting up the physical side of things. And once the SD card is done etching, we have to still prepare it, take out the files, put them in the right location, finally we get to slide the switch on the FPGA and then run the test. So that's how testing Kuiper was. And we can see how this doesn't really scale as the number of projects supported in Kuiper increases. So there had to be a better way. And automation really is necessary to scale software QA, but automation and automated testing on FPGAs is not very straightforward. So we really did a lot of thinking, like what do we want to happen? How do we really want to improve this? And we know that there's got to be a way that is fully automated and requiring very little to no human interaction as much as possible. We want to test whatever it is that we are testing, how the customers would use it. So if they have this FPGA and this FMC card, that's how we want to test it at that level. And we should be able to test things in parallel. We want to save the time. It should be flexible, whatever it is that we do, because if we want to change stuff, how things are done, it should require little to no change in the infrastructure, and it has to be reliable. Once we deploy the hardware or put it in the infrastructure, we want to make sure that we have access to it, we have connection to it. And you might ask, aren't there existing tools to meet all of this? And there are, yes, but at the same time, no, because they don't quite fit to how we want to use or what we want to make. Most automation tools are not hardware-oriented, and if they are, they don't natively support FPGAs, or if they can support FPGAs, they still require a bit of work. For example, LabGrid, it wasn't around yet when we started the test harness, but even if it does today, it doesn't really fit to how we want to do things. And these are just some of the research solutions. I think it's always not easy to say that we have completely ruled out any of these tools, especially considering how much progress there is in the hardware support for all of these. So with that, this is the generic design of the test harness. So with this design, we get to test the software at the system level. Everything is automated from retrieval from the source to loading to the board to running the test and then publishing the results. And these are the specific tools that we have used, we leveraged, or we have created. And I'll try to walk us through each block within the time. There's a lot of things here. So first is the source. This is where we get the artifacts. This is more of a design constraint rather than a design decision, because most of the source code in the company is in some version control, whether that's Bitbucket or GitHub. So we have to support it. Artifactory, that's where the builds are uploaded. It's not our choice, but definitely if we change and we are changing, moving to something else, then we're going to support that as well. And the way the tests are triggered, there are two main ways. Either from something external triggers the test, where a build pipeline, when it's done, when it's finished uploading the artifacts, it can trigger the test side. Or we can manually trigger it ourselves if we want to verify something. Another way we can trigger the test is if we don't have access to how things are done, or if we do not have any level of control to have an external pipeline trigger ours, we can look at the source and monitor the source. If there are changes there, and then we wait for the uploads to finish, and then we get those artifacts. Jenkins was an obvious choice for a test manager. And by utilizing the Swarm plugin, we have distributed runners we call agents, which are a Linux host to which boards are connected. And the agent would only be involved in a pipeline if the required hardware in the pipeline is attached to it. So if it doesn't have that hardware, it doesn't get involved at all. And we keep all that logic inside our Jenkins shared library. And the automated test process are generally defined in a Jenkins file, and we have so many stages there that we can just mix and match. Well, not really literally mix and match, because you have to do it some stages in the proper order, but just take what you need, everything is there. And even the details or the parameters that you want to do inside a container, or how you want to set up the environment, everything is abstracted and ready for configuration from the Jenkins file. You don't have to do anything else elsewhere. So we can, in Jenkins, we can choose to have multiple executors for a particular node, and that's what we leverage to run parallel tests on the hardware on a particular agent. So every test executor and board combination, when it is required, would run in isolated environments using Docker containers. So we leverage the existing tests for validation or to verify the functionality of a hardware, even if we change the files. We use the existing tests for it from different locations that are already existing. For example, some parts, like transceivers, they have their own libraries to interact with them, so we can use those. We also have MATLAB tests, so we use them a lot for the MATLAB toolboxes. But of all these, what we most frequently use and depend on is PyADI. So if you were here yesterday, there was a pretty good overview of what it is, but if you didn't, that's okay. So PyADI is a Python abstraction module for ADI hardware with IO devices to make them easier to use. So the libIO interface, although extremely flexible, can be quite challenging to begin with, especially if you're just starting with a device that you have very little familiarity with. So what we do here, so as you can see, there are these are the actual parts the company makes, the evaluation boards the company makes. So what we do is we know that these tests are passing, and we know that these reflect the actual functionality of the board. So if something fails with these tests, it's more likely that what we change with the boot files caused the failure. So that's how we use PyADI for these tests. But how do we first communicate with the board? Like, how do we know it's there? How do we move things around? How do we connect to it? So we have this utility called Nebula, where we can control, we have access to the board, or the hardware's Ethernet, the UART, the JTAG. We have control over the PDU and its power, and can download things. We can, basically it's a way to interact with the board without having to use a macro or something like that. So the multiple lines you saw a while ago in the generic design from the test executor to the board are the actual connections we have to the board. So the primary way we communicate with the hardware is through network, because that's the fastest. When we have to download, we have to copy files, we do it there. If that fails, we try other stuff. We try UART. The last thing is JTAG, because it's the last resort. And just to give us an example of what Nebula does. So for example, this is a command to use Nebula to update the files on an FPGA. So it's already running, and what it does is you just run this command and give it the parameter of a board name, so it knows which file to take out, where to put it, and it will under the hood, it will do all these stuff. So Nebula, you can find it here. Nebula, what Nebula Manager does is like what the human or what the end user would do, and then you just call the different modules under it. So here, we have access to different interfaces with the hardware. You can see the network. If it failed to do it via network, it would try to do it in UART, SD card mux, and all that stuff. So you can check Nebula there. You don't even have to have a test harness to use this. How it does this is it depends on a configuration file, so that with this board name, it knows how to interact with the board or what to do with the board. So I'll get to that later. As for the reporting and publishing the results, so we have Elasticsearch. We keep everything there. We use Kibana a lot for visualization, but we also have Constellation as a one-stop shop for everything test harness. So this is Constellation. So it's just a page we just put everything there. It's more of, we could have done this in Kibana, but we choose to do some things like outside, like the usual tools, just because we find it easier to do it. But yeah, telemetry here is a library or a Python library wherein we can just to abstract interactions with Elasticsearch better. So that's actually where Constellation should come in, because we have that tool already. We can manipulate data better and easier in the Python side. We also have support for telemetry in MATLAB. So here, for the board management, everything is there. As you can see in the hardware infrastructure, there are a lot of boards, there are a lot of connections, there are a lot of cables, there are a lot of addresses and paths. So everything is documented in NetBox. And this is where Nebula config comes in. So in NetBox, we use the data we have in NetBox to generate what Nebula needs to interact with the board. So here, this is an example of all the devices, just a part of the devices that we have. So we use the tags to know if a board should be added to a particular pipeline, the status of the board, if it's actually usable. And this particular example here for a ADI part, ADI carrier and transceiver, we use or leverage the journal tab in NetBox to know the changes in the board. So we have information there of which pipelines used it, which pipeline caused it to fail, and if someone is actually accessing the board remotely outside the test harness, it should be here. And Nebula config is generated from NetBox such that we think of NetBox as our source of truth for the status of the test harness. So before, we had to define that Nebula config. It's a simple YAML file that has a board name with all the details a board needs. And if we make changes, if, for example, I need to access the board for debug, I have to update the Nebula config on the agents, like manually, so that it wouldn't be included in the pipelines. And no one would even know that I was using it for myself. So that's why when we migrated to documenting everything in NetBox, it saved us a lot of headache trying to figure out why my screen session was not working. That's because someone else is using the same screen session, and it was just getting mixed up. So it's more of really documenting the actual status of the test harness. So again, putting everything together, this is what we have. And just to give us an example of what it can do, I'll walk us through this. I hope we can see the titles there, but so this is an example of a pipeline, a test pipeline that is triggered by an external build pipeline for the HDL output of another team. So what it first does is, well, we don't have access to, or we don't have control like when that pipeline would run. So that pipeline would be the one to trigger the test pipeline. And it was agreed upon that this pipeline would give us information of what are the projects that it was able to build. Because it doesn't build projects that there were no changes for the files. It just consumes a lot of time. So it doesn't have a fixed set of required hardware. So first we get this information that we need, and then we move on to setting up the agents, making sure everything is updated, everything is running fine. We generate a Nebula config from NetBox. Here we check if the hardware or the available artifacts are actually relevant to what we have, what hardware we have. So that is this stage. And if we have the hardware that can be tested, then we run them on the test executors. So every test executor would run the stages defined in the configuration. So from setting up the Docker environment, if you have to use different tools or different versions, it will be done here. What I want to highlight here is the check device status, even after running in the test executor, after this part. We already have a Nebula config here that should reflect the status of the boards, and then still check it again. Why is that? Because at some point, we treated all the test harness resources as just one resource. So that entire rack was treated as one lockable resource. And it wasn't really a problem because we didn't have a lot of pipelines to support. So even if a pipeline would just need one board, it would lock the entire 18 FPGAs for itself. Again, it wasn't a problem before. We had like 2 pipelines, and they weren't running simultaneously. And then when eventually we supported several others, and it just continues to increase, pipelines would just get queued, even if they don't have to use that hardware. It was a waste of time. So finally, we knew we needed to do this very long before. It's just that it would take a lot of refactoring to how we do things. So we delayed it and delayed it until finally we couldn't delay it anymore. So what this does is we have a first we have a snapshot of the hardware we can use at that time. And here we take it again, we verify that it's actually something usable, because now that we support that every board is one lockable resource, they can run now, pipelines can now run in parallel. And one pipeline can cause that board to fail, so we have to check it again if it's actually usable the time we have the lock. So that's why this is here. And these are the tests that we run. So we check if there are outstanding message errors, if there are attributes that do not look right, because those are the things from the Linux test side, those are the things that may not be apparent right away that would cause hardware functionality to fail. For example, simple device name changes. That's like, it doesn't really change the behavior of the hardware, but everything else that's built upon and depending on that device name would break. So we do those checks here. And then we compile the results, send it to Elastic, and this log artifact stage, the generated test results, like every line, every dmessage error, every PyTest failure gets logged so that we can more granularly visualize them in Constellation. So I hope that gives us an idea of what it can do. So now, this is what it looked like before. I think this was in early 2020 or even before the pandemic. So we had 3 prototypes in different locations. We used to use an RPi as an agent, but then that would be quite limiting to what tools you can install and the tools you can use inside the container. So we replaced that with Intel NUX. Now we have, this is just one of the 2 server racks that we have. We have 18 FPGAs, several RPis, and we use our own Atom 2000 for the signal sources and sinks if they're not very precise, if they do not have a very precise requirement. This is a summary of how the things are connected. So whenever possible, everything is connected to the network, but the agents themselves are connected via UART and JTAG. We have an idea of how many different pieces are in the test harness, so we need to make sure that we can spin things up reliably. So we deployed all of these as services, containerized services, and we have an infrastructure. We try to implement infrastructure as code. Right now we use Docker Compose for this, but eventually we're looking into using something else. So lifelines are like things that just make life easier when they work. Sometimes they do not work. So the USB SD MUX, so what it does is, it's a physical device that just switches over. If you're connected to an FPGA, that you can set it to use the FPGA or use it to a host. It saves us a lot of time trying to recover a failed board because we can just mount the SD card to the host and then move things around and then flip it back. But it's not compatible with every FPGA that we have. So hopefully the time will come when every FPGA that is deployed will have an SD card MUX, because that would be so much better. The SD card etcher program, so this is a script that we make. So that part where we still, the automation, everything is fully automated if you have the SD MUX. If you don't, and if we still have to re-image an SD card because there are changes in the rootfs or an entire SD card image is created, we have to etch it manually. So we just use this, we created this SD card program that if you just plug in an SD card, it would detect it and it would write it. So we got questioned, why didn't you just buy the Balena Etcher Pro? We like a challenge for ourselves. So yeah, that was a very big question that was given to us. It took us a lot of engineering hours to do this, but it was quite fun. And we made quite a mess overriding the main partition of the machine. Oh, it was a headache. But it was good. It's working, and it's very reliable now. So the plugin test support, right now, we have 18 FPGAs in the test harness, but we still have 110 and growing number of supported hardware in Kuiper. So this plugin test support enables us to have like a temporary Nebula config available for every board combination, such that, for example, there are 4 different carriers, CCU102, 706, 702, and a Z. And those 4 boards we use for plug and test, such that, okay, there's a pipeline that's waiting for plug and test. We just set the board carrier and FMC evaluation board, and the test would run fine, as if it's permanently deployed. So that definitely does help us with testing the entire support of Kuiper. Where it's currently used, so these are some of the things that we test. Again, Kuiper, RPi boot files, bare metal or no OS binaries, the firmwares, repositories. So these are sometimes, it really depends, commit-based, every commit, or every trusted user. So our pull request, the security or the level of allowed branches to run are dependent on these repositories. There's a lot left to do for the test harness. So our Jenkins shared library, we need to refactor it, because when we started doing the test harness and developing the test harness, everything, we were just in quite a rush to get things done and get things working, that we didn't think of scaling, of properly scaling. So what I mean to say is, we have this one file in our Jenkins shared library where all the stages are defined there. Not a problem. And then we continue adding more stages. And at some point, Jenkins wouldn't even compile or couldn't even use our Jenkins shared library because of this one file that was just gotten so big. So those considerations we overlooked before, but now we're facing our technical debt of actually making good plans with the development. So we're doing that. Board recovery, we still encounter failures with the board when boot files just cause the board to kernel panic. We have to handle that part. Again, if we have the SD mux, that's easy. If we don't, it's a headache. So we make sure we want to make use of Kubernetes moving forward, because right now everything is we reuse our server, we use everything, so everything's on our side is on-prem, so we don't have to worry so much about what do you call this? Yeah, everything's on-prem, so everything's easy. But we have a move now to house or locate everything in our enterprise or company-wide servers, and we're spinning up a lot of instances of the test harness, so it doesn't really scale. We just use the Docker Compose to spin things up. Yeah, so more docs, because this is the part when we just try to churn out the development and get things moving, get things along, and now when issues come up, we have no idea if or why it's happening. Is that time? I'm not sure. Not yet. No. Okay, that's okay. I was worried, because when I practiced a while ago, I needed more than 40 minutes. So that's actually all of the slides. So I think we have 13 minutes left. So if you have any questions, please. Thank you. Okay, here's a question.
Hi. You said that you're currently, your developers have to push code to your source control to start testing. Do you have plans to allow developers to test code that they haven't pushed yet?
That's a good question. So it's more of like having a development environment, like a remote access to the boards for their development.
Yeah.
We do. That's in the works. But right now, what we can do, we actually allow that to happen. So as long as we have someone tells us that, okay, they want to use a board, we give them access. So as long as we make changes in NetBox, everything's reflected there, and we can agree, okay, we can let you use this board, you can use it, but like having, like, I don't know, like a system, nothing is in place yet. It's more of, tell us, do you need this board? We'll give you the access. You can use everything, do whatever you want with it. But having a full infrastructure just for that, I'm not sure if I should say this, but so we're doing something about it, okay. At least for the inside the company.
Just slightly more of a follow-up question. You said that you can. That speaker is doing something weird.
I'm sorry.
That's all right. You said that the you can I think it's my microphone that's doing that. You said that you can, developers can develop on the boards that you have in your test harness. Do you have the ability for developers to run the same tests that Jenkins does from their desk using code they haven't pushed? That's a slightly more complicated question, I know.
Yeah. Well, it really depends on the tests that you wish to run.
Right.
So if it can be done on FPGA, then why not, right? Because as long as you have access to the board, and yeah, what I can, from a developer's perspective, if we want access to the board, we can do that now, no problem. But there's no system in place that, hey, I want to reserve this board, I want to use it. There's nothing there, but what you want to do inside the board or with the board, it's up to you. Yeah. So if you want to break it and make a brick out of it, it's up to you. But it's going to be our headache to get it back to like a usable state. Yeah.
Okay. Okay. Well, actually, I've got a question. So is Nebula based on an open source project, or is that an internal tool that you developed?
It's an internal tool that we developed.
Do you plan on open sourcing it, or?
Yes, it should be, but like the legalities or like the licenses, I think it should be open source. I'm not the one who maintains that particular repo, but it should be. Yeah.
Any other questions?
Yeah, thank you for assisting with the mic.
Now that you've put this together and it works, if you were to go back and start the project again today, how many of the pieces would you reuse and how many things would you do differently?
Oh, very good question, requiring a lot of introspection. Because right, one of the things that we're seriously looking into is, do we really need, because right now we depend on Jenkins a lot. And Jenkins, sometimes one version to another, it gives us, so many problems. So probably using something else, but again, it works. So, probably one big thing would be like the dashboards. We didn't really ditch Kibana. It's still there. We still host it, but we didn't give it a lot of effort to standardize everything in Kibana. It would have been so much easier instead of developing everything for ourselves again. Definitely that. And yeah, I think those are two big things that my teammates would be watching this, and I'm definitely going to bring back a lot of feedback from what I've seen from the conference. And there's going to be, we have our work cut out for us for sure. Yeah. Thank you.
Any other questions?
Great talk.
Thank you.
So I have a quick question. Is that like when you do some of the board testing, right? You need a hardware to connect to it, right? So most of when you design the board, so somebody have to design the connector for you, right? Or how you handle that?
Someone has to design?
And you have to design something like the outside, right? The test box outside, right? You go.
So since what we have are FPGAs, like all the ports that we need are already there. So it's just really a matter of connecting cables. But I understand what you mean. Right now, we don't need any special infrastructure to deploy the boards. But yeah, it's actually very interesting. I saw something from the Linario showcase that they have like a rig for the RPi, like to really like standardize like how they interface with the hardware. And it would be cool if we have something similar for FPGAs, but I don't know how big that board will be. But yeah, we don't need anything special, really.
Okay, thanks.
Thank you.
So you mentioned LabGrid didn't exist when you started. Would you use it now?
Yeah, okay, going back to that question, yes, we would invest more time, really, looking into like how we can use it, for sure. Because, again, everything it's more of, it's working, it's not broken, let's not touch it. But things break, and as things change, things continue to, not falling apart, but eventually, we really have to future-proof this test harness. Yeah. LabGrid, Kibana, and like Jenkins like, for automation, for sure. Thank you. Anything else? I guess that's all. Thank you. Thank you very much.